Hello again, everyone, and welcome to part 2 of our lecture on Chapter 10, Analyzing Quantitative Data. In part 1 of our lecture, we really focused on measures of univariate analysis, where we're doing a deep dive into a single variable. And we wrapped up our part 1 lecture by talking about measures of central tendency. If you can remember from that lecture, one of the things that comes up frequently with measures of central tendency is that sometimes they're influenced by things like outlying variables or outlying scores, or if our distribution just isn't quite as pretty as we want, like there might be multiple peaks and valleys in our data distribution. And you might have been wondering, like, what does that mean? What is that sort of how do we describe when that happens? And one of the ways that we do that is by measuring what we call variability and dispersion. So, in our research, measures of central tendency tell us about the middle scores in a distribution. But oftentimes, measures of central tendency tell us very little about how spread out our scores are. And because we need to know more information about how scores are spread out, we use measures of variability and dispersion to give us that information. So, in other words, variability and dispersion gives us information about how far apart or close together values are to one another in a distribution. Variability really gives us the ability to express the degree to which data in a data set is spread out or deviates from the center. So, variability is saying, here is the center point of our data. How much do we expect our data set to spread out from there? How far away from that do we expect it to be? And oftentimes when we're talking about variability, there are two types of subtypes of variability. One of those is homogeny or homogeneous, which is a data set that has very little variability. So if you hear someone say that they have a homogeneous data set, it means that their data is pretty well closely tied together. And the variables are pretty close, they're not very spread out, they're very similar. But you might also hear someone say that they have a heterogeneous data set, which is a data set that has a lot of variability. Scores are very different from one another, they range all across the board. And the really interesting thing about data, especially in comparison to how we approach a lot of the work that we do as counselors, where we're looking for variety and diversity in the work that we do, in statistics, you don't want that variety. You don't want that variability in your scores. In fact, heterogeneous groups pose a higher level of complexity in approaching our analyses. In the fact that if you have an incredibly heterogeneous sample or an incredibly heterogeneous variable, you have to run different analyses to account for that variability in scores, because many statistical analyses that are commonly used won't be applicable to a highly variable or a high variability item in a study. We also have multiple measures that we use for understanding variability and dispersion. So, one of the most common and the simplest is the range. So, the range is the difference between the largest and the smallest numbers in a data set. So, we're saying, all right, our range on a data set is the highest number possible that someone gave, from that subtracted the lowest number on our assessment. So, maybe you have a variable that measures age, and the oldest person in your data set reported that their age was 80 years old, and the youngest person reported that their age was 18 years old. So you would subtract 18 from 80, and that would give you your range. And that is basically a way of us saying, here is the total spread of our data set, like how they are in comparison from the smallest to the biggest. We also have a subtype of range, which is called an interquartile range. And an interquartile range is another measure of range that looks at the middle 50% of scores in a data set on a variable. I know that our textbook goes into a pretty big detailed description of what an interquartile range is, and I'm not going to have you know that information, mainly because very few statisticians use interquartile range because there are much better measures of dispersion and variability, namely variance and standard deviation. These are the two most common measures of variability and dispersion because they are the most robust and they tell us the most information. So, variance represents each data point's average deviation from the mean of that variable. So, in other words, the variance is the average sum of the squared distance of every single point in a data set from the mean. So, when you get a variance score, it's saying how far each data point is on average from our mean and how far we can expect that to be. And this is heavily related to our standard deviation. And the standard deviation is the squared root of our variance. And this standard deviation represents each data point's average deviation from the mean. So where a variance tells us very specifically how far a data point is from a mean, our standard deviation will say, in general, for your whole data set, this is about how far on average we expect your variables to be from the mean. So variance is very specific to a variable, and standard deviation is more broad to the entire variable data set. So for this entire variable, here's how far on average we would expect your scores to deviate from the mean, to be away from the mean. So what's interesting about the standard deviation and variance models that we use is that both of them are based on what we call a standard normal distribution. So I want to take some time to talk about what that is because it is the theoretical base that we use for understanding both our measures of central tendency as well as our measures of variability and dispersion. So a normal distribution, a standard normal distribution, is a theoretical perfect distribution where the mean, mode, and median are equal to one another in a data set. So our scores are perfectly symmetrical to one another. They're perfectly distributed in a way that the mean, median, and mode are all exactly equal to one another. We say that this data set is symmetrical in that the mean divides the distribution into two equal halves that are exactly the same on both sides. But really, this standard normal distribution is used to compare against our actual distribution. Because you might be thinking to yourself, if this is a theoretical distribution, why do we use it? Well, we use it as a comparison. We very seldomly have standard normal distributions in social sciences. I cannot think of very many variables that fall into this category. And because of that, we use the standard normal distribution as this point of comparison for understanding our data sets, our actual data sets that do not fall into this category, and saying, okay, this is about how far away from a standard normal distribution I would expect my distribution to be. Within a standard normal distribution, we have a couple of key terms that we use for understanding how that data set is sort of displayed and what the variability and dispersion is of the scores in that data set. And those are standard scores or z-scores. So standard scores are an indicator that the number of the number of standard deviations in a distribution and what proportion of those scores fall within that range. So I know that this seems really sort of vague, but the way that this works is that you have a standard normal distribution and you use a standard score to say, okay, Here's about how far away from the mean someone is based on a standard score. And the standard score, this z-score, is a specific formula that is used in statistics to say no matter what the range of your variable is, I can use a z-score, and a z-score on my study and a z-score on your study or someone else's study will be the same metric. So that's what a standard score is. It's a way of standardizing how far someone's score is from the mean of our distribution in a standard number that can be compared across multiple studies, multiple variables, even if they're measuring different things, because it's a standard score that falls on this normal distribution. So with standard scores, or also as we're referring to them, z-scores, they have very predetermined ranges of how many scores in a standard normal distribution, or the percentage of scores, will fall within that standard range. So the proportion of z-scores that fall between any number of z-scores in any normal distribution, regardless of its means or standard deviations, are defined by the following rules always. So these are the hard rules that come with the proportion of z-scores and how they fall in relation to one another. So the area between z-scores 0 and -1, as well as 0 and 1, is 0.34. And that is a decimal point of how our scores are dispersed. But the really cool thing about standard scores is you can convert that to a percentage. So what this is saying is that there are 34% of scores in a standard normal distribution that will fall between 0 and 1 standard score, or 1 z-score. And there are another 34% that will fall between 0 and -1 z-score. So that means from -1 to 1, with 0 being the middle point on the distribution where your mean, median, and mode exists, you are going to have approximately 68% of your scores between -1 and 1. If you move beyond that and you look at the area between z-scores 1 and 2 and -1 and -2, you're going to account for an additional 13% each. So you're going to have an additional 13% between 1 and 2 z-scores, and another 13% between -1 and -2 z-scores, representing that you have 26%, or a little bit over, it's actually like 27.1% of your scores are going to fall within that range. So if we add those together and we say, okay, there were 68% of scores that were between -1 and 1, and then we're adding an additional 27 points, or an additional 27% of scores, you're now looking at 95% of your distribution falling within -2 to 2 standard scores, or z-scores, away from the mean. So then, as you might suspect, the z-scores between 2 and 3 and -2 and -3 is pretty small. We're actually getting to only 2% in each of those categories. So less than 5% of our sample falls beyond 2 standard scores away from our mean. And then anything beyond that becomes increasingly smaller. It gets even smaller. In fact, we would say that the proportion of scores that are greater than the z-score of 3 or less than the z-score of -3 is less than 1%. It's 0.13% of scores that fall into that range. So this is what our standard normal distribution looks like. As you can see in this graphic depiction, our scores are generally centered around our mean. And our mean, median, and mode are exactly equal here in the middle with a z-score of 0. You have 34% of scores that fall between -1 and 0, and you have another 34 that fall between 0 and 1 standard score. Then you have your 13% between 1 and 2, and -1 and -2 z-scores, and then your 2% that falls in that 2 to 3 and -2 to -3. And up here you can see how that sort of is displayed in our standard normal distribution. 68% of scores are going to fall within one standard deviation of our mean or one standard score. 95 are going to fall within 2, and just short of 100%, 99.7 will fall within that 3 standard score range. And what you can see here is that these rules of standard z-scores mean that approximately 68% of our data points will fall within one standard deviation above and below the means, and 99 will fall within 2 above and below our means. And this is what we use as a comparison for understanding our research and being able to say, okay, this is how much my own data approximates a normal curve and how I understand it. But the interesting thing, as I've sort of briefly mentioned, is that in social sciences, we very rarely have a standard normal distribution on our variables. We probably have what's called kurtosis and skewedness. And these are ways that our distributions can sort of change depending on our data. So let's go into a little bit more detail on these. So the first of these is skewedness, which occurs when a distribution lacks symmetry that is created when the mean, median, and mode are in the center. So in a standard normal distribution, we have a completely symmetrical distribution, like this one here in the middle. Our mean, median, and mode are exactly the same. When we have skewedness, we're looking at these two examples on the outside, where we're seeing that the shape of our distribution is no longer symmetrical, it's asymmetrical. And we use the term skewedness to really describe when a distribution is either clustered on the left or clustered on the right. And a distribution that has a tail, well, actually, let me back up here. When we're talking about skewedness, I think sometimes the terms can be a little bit confusing. So there's a really cute little saying that helps with this, that the tail is in the tail, or the tail is in the tail, which I know is silly, but when I'm using the word tail the first time, it's tail like a story, T-A-L-E, is in the tail, T-A-I-L. So you have what's called a left and a right skew, which can sometimes also be called a positive and a negative skew. So in a left skewed variable, we will have a distribution with a long tail on the left side of our distribution and a majority of data on the right. So here is an example of a left skewed data. So we say that this is a left skew because the majority of data is here on the right, but the tail of our distribution, this part right here, is pointing to the left, or the negative side of our distribution, which means that we have a negatively or left skewed data set. And as you can see, in a left negatively skewed distribution, the mean will have the smallest value, followed by the median, and then the mode, which will be at the highest peak of the distribution. In a distribution with a long tail on the right, but a majority of points on the left, this is called a right skewed, right-tailed, or positively skewed distribution. So you have the majority of the scores here on the left, and the tail is pointing to the right or in the positive direction of our distribution. And in a right or positively skewed distribution, the mode will be on the left of the distribution where the highest peak is. The median will have the greater value than the mode, and the mean will have the highest value than both the median and the mode. So as you can see, when you're trying to understand what a data set looks like, we might have data sets that are skewed in some way because we're human and our scores will vary. But there also is a chance that our distribution is almost sort of changed in a different way. And we call this kurtosis. So, kurtosis is another characteristic that can influence the way that our distributions are displayed. And together with skewedness, we can see how our scores really can begin to deviate from a standard normal distribution pretty quickly. So, in kurtosis, we are talking specifically about how pointy or flat our data distribution is. So, that peak in the middle, that mode, how pointy is that mode or how flat is that mode? And there are different ways that we describe it. So, in a standard normal distribution, we call this mesokurtic, saying that it is standard and normally distributed, which I know is a little bit hard to see, but it's this yellow distribution here in this model. That's a mesokurtic distribution, and that's what we are looking for. But we can also sometimes have high peaks with long, flat tails. And when that happens, we have what's called a leptokurtic distribution, which is this blue pointy one here, where you have a really high, tall peak in the middle and these long tails on the side. And that's, again, that leptokurtic distribution. But we can also have what's called a platykurtic distribution, which is this green example here, where you almost have a plateau in your scores. There's no true mode because it sort of just like flattens out at the top, and there are these very short tails on the side. And kurtosis as a whole is an indication that there are some problematic outliers that are present in our distribution. So, if kurtosis is noted during analysis, as a researcher, we will often take this information into account and look at the distribution to possibly figure out a way that we can remove our outliers and bring our data set to a shape that's closer to a normal standard distribution. And there are different statistical ways that we can do that, that we can sort of not account for those outliers or account for them in different ways. That's a little bit beyond the scope of this class, but we use kurtosis to understand how we need to work with our data. So, continuing on our measures of variability and dispersion, there are a couple of characteristics that come up or definitions that are helpful for us to know. And the first of those is what we call continuous and discrete variables. So, discrete variables are specific categorical variables that can only take whole numbers and do not have any continuity in terms of measurement. So, a couple of good examples of discrete variables are if we're looking at the number of employees in an institution. You can only have whole numbers. You can't have half a person at an institution. And that whole number doesn't have any continuity of measurement. So, what that means is 5 employees at a small business is not the same as 5 employees at a Fortune 500 company. So, there's no continuity in measurement, and that they mean different things in those studies. So, discrete variables is a type of variable that we use for understanding sort of what is going on in our distribution. But we also have continuous variables. And continuous variables is a type of numeric variable that can take all possible units. So a continuous variable can be displayed in decimal points or fractions if needed. And good examples of this include income, height, and weight. And these are really the different ways that we understand the types of variables that we're working with. And you might be thinking, like, why are we talking about this? Well, we're talking about it because the types of variables that we work with will influence the way that we understand our measures of variability and dispersion. But also, once we know our measures of variability and dispersion, our types of variables, specifically discrete and continuous variables, will pave the way for understanding how we want to graphically represent our data, which is the next piece that we're going to talk about. So, a graphic representation of information in a study can have a powerful impact on a broader audience of our study because graphic representations are visual depictions of the relationships and patterns that we have in our data. So, oftentimes we use graphic representations to establish a wider base of people who can understand our research. And there are different types of graphic representations that are particularly common in quantitative studies. The first of those is the bar graph, which there's an example here on the slide as you can see. But a bar graph uses vertical bars that represent each variable in a study. And each variable in a study is represented on the bottom axis here, which is oftentimes called our x-axis. So each column represents a different variable, and our value on the left is which is our y-axis over here. Our vertical axis is our y-axis, and that shows us how that score is in comparison to whatever our metric is. So in this example, it is a frequency, so the number of students who report having a birthday in that month. So we can use a bar graph to really help our viewers or our readers easily distinguish not only which category occurs most frequently, but we can also use bar graphs to compare between other categories. So see, okay, yeah, I can see here that the majority of students have June birthdays, but like look at this in comparison to other months. There are a few months that have pretty high birth rates and then quite a few that have pretty low birth rates. So using this as a comparison to really see how her scores are in comparison to others. Another graphic representation of data that's common is what we call a histogram. And a histogram is often used in quantitative variables where categories of our variables are related to one another. So in a histogram, we're really looking at presenting the frequency of a variable in the form of a distinct but connected bar. So on the screen is an example of a histogram. So what you're seeing here is a graphic representation of one single variable. That variable is associated here on the x-axis on the bottom, which happens to be the arrival per minute. So how many minutes it took someone to arrive at whatever location they were going to. And then the left column, or x-axis, is the frequency. So how many people selected each option. And we use histograms specifically when our variable for comparison, each level of it is related. So in this example, we have a variable that increases in a standard normal way. This is a true interval data point where you have a number of minutes. There can be a true zero, an absolute zero, and an increase makes a difference in a very standardized way. So a histogram is a frequency of saying how many people selected this answer, how many people selected this one, so on and so forth. And we use histograms differently than bar graphs in that the columns of a histogram are directly beside each other. The only gaps that you see occur because no one selected that option. But there are no gaps otherwise because the answers to this variable are related to one another. They are related, they build on one another, so the bars need to be represented as such. Another example of a graphic representation of data in quantitative studies is the line graph, where you use a line to connect points in a distribution to explain change in variables. So line graphs are useful in depicting two or more categories simultaneously, or if there are multiple distributions in the same category. So, in other words, we use a line graph in an effective way to demonstrate the relationship between variables. So, changes in a variable over time, looking at how we would expect this variable to change or not from one data point of collection to the next. So you're looking at a variable that is in multiple categories and you're trying to track change over time. That's when you use a line graph. And finally, we also have what's called a pie chart. And a pie chart is a visual representation of the distribution of one single variable. And pie charts work best with categorical variables that have a small number of categories. So, the main advantage of a pie chart is its visual impact on the audience. When you're using a pie chart, you're really helping your audience to understand one single variable at a time that may not have a lot of distribution but is meaningful. And you want to display that in a way that makes sense. So, a pie chart can be really helpful for taking that deeper dive into a single variable. So that is where we're going to wrap up part 2 of our lecture on chapter 10. Join me for part 3 of our lecture, where we're going to continue talking a little bit in more detail about specific analyses that you can run in quantitative studies and how those sort of influence the way that we interpret the results of our study. I will see you all in the next lecture.